The next major mode of action of alcohol is when it acts as an electrophile. From last time we mentioned that alcohol is a poor electrophile. This is because when alcohol reacts with nucleophile, one possible way for it to react is nucleophile attacking on the carbon, kicking out the hydroxyl group, leading to the formation of R nucleophile with hydroxide. However, this hydroxyl group and hydroxide is a very poor leaving group. Therefore, the attacks of nucleophile here is not very favorable, and therefore you need to activate the hydroxide into a better leaving group. So this can be solved by activating alcohols into a better leaving group. For example, protonation of hydroxyl group with an acid. This will create OH2+, which is a better leaving group because when you react it with, for example, a halide, kicking out this OH2+, becoming water. This becomes a good leaving group because water is stable. And therefore, this protonated alcohol becomes a better electrophile. So I would like to emphasize the concept that for base, if you put in the reaction, it can activate nucleophile by making it more nucleophilic. For example, changing from alcohol to alkoxide. And for acid, you can use it to activate electrophile as well as leaving group. For example, you can activate hydroxyl groups into OH2+, which makes it a better leaving group and becoming water when you kicked out. Or you can activate alcohols into a better electrophile as well using acidic conditions. The first reaction, you might have seen it before, is the dehydration of alcohols to form alkene. You might have seen it in the synthesis of alkene, right? But this is the emphasis on how acid can make alcohols becoming a better leaving group. By first, when you have an alcohol, you can use oxygen lone pair to attack acid catalyst to become a better leaving group. Which can get kicked out, and then you can remove the proton, the nearby proton, to form the alkene. Okay, so dehydration means removal of water, because in this process you lose a molecule of water as a leaving group. And the dehydration is reversible process because you can also add water back to the alkene. And in this case, Conc sulfuric acid or Conc phosphoric acid is the most commonly used acid, and you can use it as both acting as acid catalyst and also the dehydrating agents. For the mechanisms, let me repeat again. Normally it will proceed by E1 mechanisms where, for example, if you have this alcohol, you need to activate the hydroxyl group into a better leaving group by protonation first. This will create the OH2+, which is now a good leaving group. And from here, you can, if you heat the reaction up, the bond between carbon and oxygen will break, and you lose a molecule of water to form a carbocation here on the carbon. And this carbocation intermediate can undergo rearrangement if possible, but this is probably too deep. So normally it will, you can remove the proton using some species in the reaction, for example water itself, or some something that already have the lone pair like hydroxyl group from the alcohol. This can abstract the nearby proton and then feed in electrons to the carbon-carbon bond. At the end, you will form a double bond between these two carbons. Okay. And if you have more than one type of proton nearby, for example, in this case, you have this type of proton as well, it is possible that your base will abstract the proton here, giving the alkene at this position instead. So you have two types of products that might be able to occur, but since the alkene is more stable when you have more substituents around it, therefore this one is the major type of product because the alkene formed is more stable, and this is the minor product that you form. Okay. So if you look at this example, the alcohol reacts with acid, and then you are going to form this intermediate as you protonate the alcohol. After that, you lose the water molecule in order to form this carbocation intermediate, and you have two types of protons to eliminate, but the one that gives more stable alcohol is the one internal hydrogen here. So at the end, you are going to get the product, the alkene here inside as a major product. The next one, the alkene reacting with water and under acidic conditions. First, the alkene is slightly nucleophilic, and it will react with a strong electrophile and acid through the terminal carbon, because if you do this, you are going to generate the carbocation here inside with 3 substituents, so tertiary carbocation. Instead of if you attack inside, you will create the primary carbocation here. And we know that the tertiary carbocation is more stable than primary because there are more substituents around the carbocation. So from here, water molecules can act as a nucleophile to attack this electrophile, and then after losing proton, you will generate tertiary alcohol here. Okay, so once you got this product, the alcohols can react with acid under heat to undergo elimination. So first of all, you are going to protonate the alcohol to form a good leaving group like this. So this good leaving group can be kicked out, forming the stable carbocation again. So same thing here. From here, you can eliminate, there are 2 types of protons around it. So the one inside the ring and the one outside. If you remove the proton here, you will generate the more substituted alkene. So this is the major product of this reaction. So you can see the alkene can be migrated by addition of water and then removal of water at the end. Next, you can also convert alcohols into alkyl halides by the reaction with halides as a nucleophile. For the primary alcohols, it will undergo by SN2 mechanisms. So first of all, same as the elimination, you need to activate the alcohol group into a better leaving group by protonation first, and this will form the OH2+ as a good leaving group, and now you got the good electrophile. And from here, unlike the elimination, in this case you have some good nucleophile. In this case, this is the bromide group. This is a good nucleophile that can attack the carbon that connects to leaving group, kicking out the water, okay, and you will form a new carbon halogen bond, which is the alkyl bromide that you want, okay. And this process is called Sn2 because the nucleophile attacks at the same time as the leaving group leaves. And this is better for primary alcohols because there is less steric, so nucleophile can attack straight away as the leaving group leaves. For secondary and tertiary alcohols, they are more steric, so instead of nucleophile attack straight away, first of all you need to so for example, tertiary alcohol, the same thing occurs where you protonate the alcohols with acid to generate the leaving group. So now you have a good leaving group, but in this case the bromide cannot attack straight away because otherwise it will got blocked by these three alkyl groups. So what happens is that the water leaves, same as elimination, right? So it will generate carbocation like this, and from here there is less steric, and this is much more reactive. And now the bromide can attack, and then you form alkyl bromide that you want, okay. And this is an SN1 mechanism because there are two processes, elimination of leaving group and attack of the nucleophile. Unlike SN2 where there is only one process, the nucleophile comes in the same time as water kicks out. Okay. If you compare between bromide and chloride, you will notice that because chloride has higher electronegativity as well as the lone pair is in the lower shell than that of bromide, therefore bromide has higher nucleophilicity than chloride. And when you want to convert alcohols into alkyl chloride, using HCl might not be enough, so you need to use some extra help. In this case, you might use zinc chloride instead of HCl. The advantage here is that you have zinc 2+ as a Lewis acid. This operates similar to that of proton but stronger. So first of all, the lone pair of oxygen can attack zinc 2+ to form a much better leaving group here with oxygen. The oxygen has positive plus, so therefore this species is a strong leaving group. And after that you can kick out this whole species as a leaving group and form carbocation, and from there the chloride can now attack and then forms the alkyl chloride. The rate of the reaction can be measured, and then you can use it to predict whether the alcohol is primary, secondary, or tertiary. Because for primary alcohol, it needs to proceed by the SN2, and the reaction is not very fast because chloride is not a good nucleophile, so it cannot attack very well. For secondary alcohol, it proceeds by SN1, but the carbocation is not as stable as that of tertiary alcohol. Therefore, tertiary alcohol will react fastest. It will occur in only 1 minute, and you might observe the formation of alkyl chloride, which is not soluble in water. That's why it makes reaction mixture becomes cloudy in less than 1 minute. But for secondary alcohols, it may take about 5 minutes in order to generate alkyl chloride. So this is called Lucas test, to easily test whether your alcohol is primary, secondary, or tertiary alcohol. So we can transform alcohols into alkyl halides by using some combination of Lewis acid like proton and the halide itself. However, there are some limitations. For example, normally it only works with tertiary alcohols. With primary and secondary alcohols, the reaction doesn't proceed very well because the E1 mechanism is not very good. Because for tertiary alcohols, you can create stable carbocation, tertiary carbocation. Therefore, it proceeds much faster for tertiary, but not as good for primary and secondary. The second limitation is that once you form carbocation, instead of X attacking the carbocation, sometimes you might end up by deprotonation and then got the eliminated product as an alkene. So there are side reactions that might occur. And the carbocation might undergo rearrangement into some other types of product. And another major drawback is that you need to use a strong acidic solution. So for example, H+. And in this case, many nucleophile is not compatible with the acid because it is also basic. For example, if you have nucleophile minus species, instead of it attacking the carbocation that you form, it will instead protonate it to form the protonated species of the nucleophile that is not reactive anymore. So for example, in this case, if you want to use terminal alkyne with the negative charge on the carbon, so this is the carbanion, okay? If you want to use this as a nucleophile, instead of it attacking on the carbon in the SN2 fashion, it will protonate itself under acidic conditions, either with the proton or with the protonated alcohol, and now you form this terminal alkyne with no nucleophilicity anymore. Okay, so because you destroyed the negative charge, and now the reaction won't occur, you end up with the alcohols that you start. Okay, so in order to avoid this issue, you need to use some other activating reagents, and I will introduce you in the next few slides. The first type of reagent to activate alcohols into a better leaving group is phosphorus halides, which is much better way to make alkyl halide from alcohol. So if you look at the first example, alcohols with PCl3. If I draw the mechanism out, from alcohols we have the lone pair, so the oxygen here is a nucleophile, okay? And PCl3 is phosphorus with 3 bonds to the chlorines. And from electronegativity, we know that phosphorus is going to be electrophilic because it connects to 3 chlorines which have high En, and they are good leaving group as well. Okay, so first of all, oxygen is going to form a strong bond with phosphorus, and you are going to attack using lone pair of oxygen to the phosphorus, kicking out the chloride, and then you are going to form OH plus with PClCl like this. Okay, and this whole group is now a good leaving group. So you use PCl3 to activate the alcohol into a very good leaving group. And now if you have a chloride from that you kicked out just now, it can come back to attack the alkyl group and kick out this leaving group. At the end, you will form an alkyl chloride with the leaving groups left. So you can repeat this 3 times to form POH3, okay, as a side product. So this produces good yields of most primary and secondary alkyl halides, but not very good with tertiary alcohols because the reaction proceeds by SN2 reaction that requires the chloride to attack at the same time as leaving group leaves. If you look at these examples, starting from an alcohol reacting with PBr3, the alcohols can attack phosphorus, kicking out bromide, and you are going to form this species. So this can act as a leaving group, right? And the bromide that you just kicked out can act as a nucleophile to attack this carbon and kick out the leaving group. And from here, you just form the carbon bromide bond. Okay, so you just convert an alcohols into alkyl bromide cleanly with PBr3. The next the next example is very similar. You create the formation of bond between oxygen and phosphorus, kicking out bromide, forming this intermediate. And here again, this is a leaving group. The bromide that got kicked out is now a nucleophile that can attack this carbon by SN2 reaction, kicking out the leaving group, and then you form alkyl bromide here. If you compare between first one and second one, you might think that the first reaction should be faster because this is primary carbon, this is secondary carbon. But actually there is some factor from nearby groups as well, because for example here you have steric hindrance of this bulky group as well, but this is beyond what we want, beyond the basic chemistry, so let's ignore this for now. Okay, the other way to activate alcohols into a better leaving group is to convert it into a tosylate esters. So if you start from hydroxy group, which is not a good leaving group at all, you can use it to react with tosyl chloride, which I will mention again what it is later, kicking out chloride and forms the tosylate, which is now a very good leaving group. Okay, and if you have many types of nucleophile, you can use it to attack this carbon that connects to the tosylate group and kicks out the tosylate and forms a new bond between the nucleophile and carbon, okay, by the substitution reaction. So tosylate has the structure like this. Okay, so the alcohol can attack the sulfur, which is electrophilic because it connects to some electron withdrawing groups like oxygen and chlorines, and you have the leaving group here as a chloride. So when alcohol attacks, you can kick out the chloride and remove the proton with some base like pyridine. Okay, and then after that you form the ROTS, or the structure like this, as a leaving group here. Okay, once you form tosylate group, this is quite stable. You can isolate it and use it to react with many types of nucleophile. In this case, I picked iodide as a sample of nucleophile. The iodide can use the lone pair to attack the carbon, which is now electrophilic because it connects to the leaving group tosylate. Okay, and then it will attack by SN2 reaction, undergo inversion of stereochemistry, but that's probably too advanced. Anyway, you can replace the tosylate group with nucleophiles such as iodide. Okay, and the tosylate ion is a very good leaving group. This is because the negative charge that you forms on the oxygen can delocalize into two other oxygens. Okay, so you can draw the resonance structures from this minus on the leftmost oxygen, delocalize into the top oxygen, and also delocalize into the bottom oxygens. So these three oxygen can share the negative charge and makes the overall anion very stable. Okay, that's why tosylate ion is considered a good leaving group. And the nucleophile that you use can be many other things apart from iodide as well. If you look at this example, starting from alcohols, if you put sodium hydride, you can remove the proton from the alcohol to form the alkoxide species, which is nucleophilic at this oxygen. For the bottom reaction, alcohols can react with tosyl chloride by attacking of lone pair of oxygen to the tosyl group, kicking out chloride with the pyridine as a base to remove this proton later on. You can try to draw mechanism by yourself, but overall you will get this molecule with the tosylate group as a leaving group, therefore making this carbon becomes electrophilic. Therefore, if you heat these two molecules up, the oxygen minus can now attack this carbon, kicking out the tosylate group by SN2 reaction. Then you are going to form the bond between this oxygen with this carbon, okay, or an ether group. From here, if you put some water under acidic conditions, you are going to protonate on the left hand side because you will generate the carbocation, secondary carbocation, which is more stable than the primary carbocation. So this is now electrophilic at this position, and water can now attack in order to form the alcohol. At this position. Okay, so from here with PBr3, the alcohols, I forgot minus proton here as well, the alcohols can act as a nucleophile to attack phosphorus, kicking out bromide, and this you will form the activated species of the alcohol. Sorry. So this becomes a good leaving group, and the bromide that you formed can now act as a nucleophile, attacking this carbon, kicking out this leaving group, and then the product that you got is this. Okay. As for summary of this lecture, we can consider this carbon next to hydroxyl group as an electrophile, but if you haven't activated yet, the nucleophile cannot attack because the hydroxyl group is not a good leaving group. So you need to activate by some other reagents, for example, acid, phosphorus reagents, torsyl chloride, or zinc, or Lewis acid, and you can generate the activated species where this carbon becomes much more electrophilic, and now the nucleophile can attack and kick out these good leaving group. So this one kicked out as water, this one kicked out as oxygen connects to phosphorus, which is stable, this one kicked out as tosylate species, which is stable. So at the end you can form with nucleophile, where nucleophile can be halogens, it can be alkoxide, it can be nitrogen species, and many other things as well.